Assalamualaikum and very good morning to everyone. How are you guys? As you can see in the screen, I'm preparing this early in the morning. Okay, so we have lab number 8. Okay, our last lab module for Matlab and Simulink. So here what we're going to do, we're going to simulate the PID controller tuning. Okay, a little bit different from previous one, whereby previous one we just decide what is the value of P, I, and D, and then we test for 3 value of P, P1, P2, and P3. Same goes with I1, I2, and I3, D1, D2, and D3. And here, what we're going to do is the same thing. We're going to find the PID value, okay, PID value. But here we're going to do a tuning whereby we can find these 3 values simultaneously at the same time. Okay, compared to this one, we just try and error each of the value. But here we're going to find all the 3 value PID at the same time simultaneously. Okay, so what we have here, we have temperature control system. This is a heat exchanger. You did learn a heat transfer previously. So we have here the CV, okay, the temperature, the outlet temperature for heat exchanger is our CV. And then we have steam pressure as our manipulated variable. Okay, so just take a look where the control valve located. There will be that stream would be the manipulated variable. Okay, and then we also have the inlet as the disturbance dv, inlet to this heat exchanger as a disturbance. Okay, so we have a control loop here. Okay, the temperature sensor and transmitter will send a temperature here, and then sending a signal to a temperature controller. Okay, so this temperature controller will compare the value of temperature set point with the value of T2 measured. If there any error, okay, if there any error, it will send a signal to the transducer, so that this transducer will convert the electric signal to the pneumatic signal. Okay, it convert electrical signal to the pneumatic signal, so that it will this control valve will further open or further close. Okay, so again we have a feedback loop. Okay, we have a feedback loop. Okay, I don't know why this writing become like this. It's not really, it's too sensitive or not sensitive. Okay, we have a feedback loop here whereby we have a process. Okay, this is process. Okay, all this is a process, and then we have a controller, we have a transmitter, okay, and also a final control element, which is a control valve. Okay, so this is the our case study, and then you can read this explanation. Actually, I already mentioned that. Okay, and then again, I believe you already know about this. When a transmitter, transducer, control valve have negligible or fast dynamic, meaning to say the value of tau m is approximate 0, tau ip also approximate 0, tau v also approximate 0. Okay, I might forgot to mention previously, when dealing with transfer function, okay, when we have a transfer function, let's say the first order transfer function is like this. Okay, so this is called gain. I believe you already learned this in class. And tau is the time constant, and it represents the dynamic behavior. dynamic behavior. Okay, when the value of tau is big, okay, it have a slow response, and vice versa. When it's very small, it the system or the equipment itself having a fast response. Okay, so the second one is you are being given the closed loop transfer function. Okay, closed loop transfer function is represented by this second order transfer function. So what is the difference between this one and previously? Previously, you've been given the value of Kp, Km, Kv, but here you've been given the overall transfer function. Okay, meaning to say it's actually last time you have feedback loop, something like this, when you have a controller, GC, GV, and GP. Okay, so you also have GM, which is a transfer function for transmitter. Okay, and you did draw this in your lab number 7. Okay, so each of the element having its own transfer function, but here you have only one transfer function, so meaning to say this transfer function, okay, this one, and this one is combined. It's combined. It's already been combined, so that it only left closed loop transfer function. Okay, closed loop transfer function. So a new diagram that you should draw will be a simplified version, which is this one. You're going to have a PID, and then just put that transfer function. Okay, this one. Okay, this transfer function. Just put this transfer function. Okay, just put this one, and then we will need another block that called time delay, and later on we put a scope. Okay, plus minus. Okay, this is, we call it a delay, and this is the transfer function, the closed loop transfer function. Okay, which is this one. Okay, as I mentioned previously, this one, okay, this value is a time delay. It is a time delay, meaning to say the system have a delay about 2 seconds before it start to respond. It's actually the same meaning as when I'm asking you a question, you took some time to respond, maybe due to the internet connection. That is also called time delay. Okay. Okay, for the result and discussion, what you need to do is you have to develop a feedback loop block diagram, but this one using figure number 6.36. Okay, let's go back to figure 6.36, which is this one. Okay, this one. So this is figure 6.36. Okay, so you just replace this transfer function with your asking you to have, okay, just replace this transfer function with the transfer function given, but you have to find your own value of a b square plus cs plus 1, right? That's the transfer function given in this lab. Let's go back and take a look, which is this one. Okay, this one. Okay, So it is a exponential negative 2s over bs squared plus cs plus 1. Okay, what you need to do for different group, please make sure that, please make sure you choose different value of A, different value of B, and different value of C. You can choose any value of A, B, and C. Just make sure each one of you, not each one, each group have different value. Okay, because it is an open-ended lab whereby your result, the response should be different. Okay, for my case, I choose A equal to 4, B equal to 3, and C equal to, C equal to 6. Okay, and then we need another block here. It is called transport delay. Okay, in a Simulink, it called transport delay. And then that is to represent this section, exponential negative 2s, okay, represented by this transport delay block. Okay, so let's do this in our Simulink. Okay. Okay, let's do it in our Matlab and Simulink. Go to Simulink, start with a blank model, and then start with this sum. Start with, you can choose any block first. Okay, there is no fixed sequence for you to choose. Just make sure that you choose a correct one. Okay, I'm going to need a step, a sync, which is the scope. Okay, I would need a PID controller, PID. Okay, and then another mat operation. Okay, step here. Okay, so previously we are not using this block, but this time we're going to use it, which is, it is a delay. Just type delay and take this transport delay. Okay, this transport delay is something to cater with the time delay. Okay, and then I will edit my transfer function first. Okay, which is, it is 436. Okay, 4 3. Okay, 6 and 1. Just make sure it have 3 coefficient because it is a second order. Just click OK, enlarge this. Okay, so that we can see the value. And then we need to copy and paste. We need to copy this for the disturbance change. Okay, for the transport delay, just double click and put it as 2. Why 2? Because here we have negative 2. Okay, negative 2, so you put it there 2. Okay, and then another step. Okay, connect all the block. Okay, it's connected here and here. And for this one, make sure you change the sign first, plus, minus. Okay, and connect it to the scope. And then for this one, make sure you drag from here. Okay, before the scope, not before the add button, which add block. Okay, so make sure it's correct. Okay, so you now complete your feedback loop. Okay, which is this one. Okay, which is the develop the feedback loop. Okay, so you need to propose your own value of A, B, C. Okay, just make sure you use each of the group uh, using different value of A, B, C, and then simulate PID tuning Ziegler-Nichols closed loop tuning method. Okay, this is a standard method used in industry. Okay, and so let's simulate that PID tuning. Okay, we go back to this Simulink. Okay, the first thing you need to do is, okay, you can refer to the section, the theoretical section above on the early version of your lab module, which is this one. Okay, this is the Ziegler-Nichols closed loop tuning, whereby you need to start with step number 2. Okay, so PID tuning basically is, in a simple word, okay, it is a step. It is a step to find the best value of P, I, and D. Okay, that is, we call it as a tuning. PID tuning. Okay, to find the best value of PID tuning, so that the response, okay, so that the response is we get a desired response. Okay, so this thing you're going to learn with me in a class, maybe on the last week before we end of this semester. Okay, still a long waiting for you. Okay, but here I just want you to be clear that PID tuning is a step to find the best value of P, I, and D for that specific case. So in industry, basically they do, when they have a machine, okay, they have a real machine, so they do at that real machine or plant. Later on, you going to do the same for your lab number, for your temperature and for your pH. You're going to do the same PID tuning. Okay, but here we use a software to do the tuning. Okay. So we start with step number 2. Okay, because of the step number 1 only applicable in a real, when we have a real plant or a real pilot plant, okay, or we have a real equipment. Okay, that is for the step number 1. We have to wait until the response reach steady state, the process reach steady state. Only then we can do a PID tuning. Later on, you will see this in your temperature and pH control system lab. Okay, so what you need to do is we go back to this Simulink. Okay, we're going to do step number 2. Okay, we start with the value of Kc, or the value of P, small value first, and then we start to run. Okay, we start with PID setting, make it as 0.50. Okay, and then click OK and click the run button. Okay, seems to be it have some error here at the transport delay. Okay, this is 2. Click OK. Another one, put it as 2 also. Okay, so try to run again. Okay, it should be fine. Okay, so check on the response. Okay, as you can see here. Okay, as you can see here, the simulation time is 10. Therefore, we cannot see what happened after uh, after time equal to, after 10 seconds. Okay, so we have to increase this. Okay, just increase it to 30. Okay, and then start to hit the run button again and take a look on the response. As you can see, here, there are another step that I left. Okay, which is, as you can see here, okay, for the step, it is at 1, the step time is 1 second, and then another step time should be at different time. Okay, should be after the first step been introduced. So we can make it maybe at 15. Okay, because our simulation time is 30, so I want to make the second step input at time 50. So we click OK. So we hit the run button again. So as you can see, when the first step been introduced, this is the response, and this is when another step been introduced. Okay, what we want actually, we want to have a relation like this. Okay, we want the response to be sustained. The response should be sustained like this. So what we need to do is, okay, I should clear on this. Okay, so keep on trying. Try to increase the value of P. Okay, I want to increase it to 2. Click OK, and then hit the run button again and take a look on the response. Okay, if you saw a response like this, okay, it's getting bigger like this. Okay, if the amplitude is getting bigger, meaning to say the value of P is already too much, so you have to reduce it. Okay, so I'm going to reduce it to 1. Okay, so don't get confused. The first time I try 0.5. There is no oscillation. Then I increase to 2. That is over. So I reduce it back to 1. Okay. Okay. Let's take a look. Okay, as you can see, there are, we can say the oscillation is started. Okay. If you get this, I would suggest you to, okay, I would suggest you to increase your simulation time so that you can see what happened next after after time after 30 seconds. What happened? So let's increase the stop time, the simulation time. Let us increase to 100. Okay, increase to 100 so you can see something like this. Okay, so as you can see, the oscillation are there, but we want it to be a sustained oscillation. What does it mean by sustained? It means that it have the same amplitude. Okay, it have the same amplitude of oscillation. Okay, it should be something like this. Same amplitude here. Okay, I'm sorry that I'm not good in drawing. So it should be the same amplitude. Okay. So let us try again, but we are already near to that value. So maybe I can put it to maybe 1.2. Okay. So take a look on the response. Okay. It is getting bigger. So make sure you choose lower than that. Okay, maybe 1.1. Okay, as you can see, it's near. So you can increase the value of P to maybe another decimal places. Increase to 1, 1.115. Okay, it also too much. Make sure you reduce it. Maybe 1.12. Okay, so it seems to be okay. What if I reduce it to 1.11? Okay, it's also acceptable. If your response is like this, it is acceptable. Okay, so the value of P is 1.11. Okay, the next step, what you need to do is the value of KC. Okay, you get 1.115, 1.11. Okay, that 1.11 is actually the value of KCU. Okay, it's actually the value of KCU. So to calculate the PID setting, okay, you have to calculate using a formula like this. Okay, this is a Ziegler-Nichols formula. So the value of P you already got 1.11, and then you can calculate the value of I and D. Okay, how to calculate the value of I and D? You will need the value of PU. Okay, to calculate the value of KC, to calculate the value of, okay, first time you got P equal to 1.11, this will be equal to KCU. So according to this table, okay, according to this table, what you need to do is to calculate the value of KC, you need the value 0.6 times 1.11. Okay, how much do you get? Just press on your calculator 1.11. You will get 0.666. Okay, and then to calculate the value of tau I, it's basically tau I is equal to PU over 2. So what is the value of PU? The value of PU, okay, as you can see here, the value of PU is actually the distance between these two peaks. Okay, so to do that, you will need, just click on this symbol. Okay, just click on this symbol. Okay, as you can see here, okay, I want to enlarge this. Okay, click on that symbol, this symbol, and another one is this one, so you can drag. Okay, so you can find the value of, you can find the distance between this point to this point, which is this one. Okay, so from 6.66.3, which is here, and another one is at 75, which is here. So the distance between these two lines is actually 8.697. So this value will be the value of PU. Okay, so the value of PU will be 8.697. Okay, so you can calculate the value of tau I. It's actually 8.967 divided by 2. So what do you get? Okay, what do you get? Press on your calculator. 8.692 divided by 2, you get 4.3485. Okay, and then how about the value of tau d, which is the p tau d, basically the pu divided by 8. So just take that value, 8.697 divided by 8, you get the value of 8.697 divided by 8, you get 1.087. Okay, I just took the 4 decimal places, 3 decimal places. Okay, so you are now getting the value of Kc, tau I, and tau d. Okay, so next, what you need to do is you need to test. So make sure you show all this calculation in your lab report, and then the next thing to do is just test on that value. Okay, so we just test all the Kc, tau I, and tau d value into your system again. Okay, so put it here, 0.66666, and tau I is 4.3485. Is it? Okay, and tau d is equal to 1.087. Okay, click OK, and then click Run button again. So let's see the response. Okay, I should remove this one. Okay, if you key in directly, you will get a response like this. Okay, a response like this. Okay, so what you need to do next is for the value of I, okay, for the value of I, you need to take it as 1 over tau I. Okay, so 1 over 4.3485. Do you get the value of 1 over 4.3485? You get the value of 0.3. Okay, substitute it into 0.3. 0.23. Okay. Okay, the question is why we need to divide. Why we need to take 1 over tau I. It is because of the equation of PID. Kc is equal to 1 plus 1 over tau I plus tau ds. Okay, so this is the value of P, value of I, and the value of D. So for the value of I, we should take this one. Okay, so let us take a look on the response. Okay, let's see the different. We should get different response. Okay, so click OK. You can straight away hit the run button from here. Okay, just click this and okay, so you will see a response like this. Okay, so if you get a response like this, what you can do is you have to increase to make it better response. You just need to change the value of step, this meaning to say the disturbance being introduced later. Okay, try again. So you can see it's better. It's something like this. Okay, so this one is for the okay, maybe you are not that clear. Okay, so this is the response for step change, and this is the response for disturbance change. So next, what you need to do again, calculate the rise time, the settling time, the overshoot. Okay, the overshoot, the period of oscillation for this response. Okay, and that's it for lab number 8. Okay, I think you might be confused about all the steps. Okay, so I would like to summarize for you. Okay, the first thing to do is construct your feedback loop. Okay, construct the feedback loop. I believe you know how to do it. Feedback loop diagram. Okay, the second one, choose the value of A, B, and C. Any value, don't worry. Okay, any value. And then the third one is you need to start with the value of P, very small value of P. Okay, you should, maybe you can start with the value of P equal to 0.5 and then increase further until you get a sustained oscillation. Okay, and then after you get a sustained oscillation, what you need to do is you have to calculate the value of PU, okay, which is the distance between these two peaks. Okay, calculate that. Okay, I wrote it here. Calculate. Okay, Kc will be equal to Kcu. Okay, so you have to calculate the value of Pu, which is the distance between this line. Okay, so the distance here in the unit of time. Okay, and then once you get the value of Kcu and Pu, you need to use a Ziegler-Nichols formula, just like in this table. Okay, which is this table. Okay, this table. Okay, so use this formula. Okay, okay, use this formula because you want to get the value of PID. Okay, so use this formula. So use that formula. P is equal to 0.66. 0.6. Okay, P equal to 0.6 Kcu. Okay, and then I is equal to Pu divided by 2, and then D is equal to Pu divided by 8. And then another continue with substitute the value of PID into your PID controller at your system. Okay, and then for the value of I, make sure you put it as 1 over I. Okay, and the value of the last one is take a look on the response. Okay, you should get a good response. Okay, something like this. Okay, and then after you get that response, make sure you calculate the, should be something like this. So don't forget to calculate the rise time and the settling time together with how much the overshoot are there. Calculate it for both set point change and disturbance change. Okay, what does it mean by that? It means that, okay, when you have a response like this, and then you have another step here like this. Okay, so this first, okay, this section is for the set point change, and this section is for the disturbance rejection. Okay, so you need to calculate a rise time here and also a rise time here. From here to here, the rise time. Okay, the rise time 1, and another rise time 2. Okay, so you compare which one is better, which one having the lowest value, which one having a lower value, which one having the higher value. Is it the set point change? Is it the disturbance rejection? Okay, and then about this, okay, about this block also represent a disturbance rejection. Sorry. Okay, this section of block diagram, okay, this section of block diagram represent disturbance rejection, and this section, okay, from here to here, okay, it's represent set point change, and this one is disturbance change. Okay, so later on you're going to learn this with me in a class. Okay, so don't worry. So I think that's all for this lab. I wish you please have watched this video till the end, and then good luck for your next lab session. Thank you.